Now, angular momentum of system of particles, this article we have to study. In here, I am consider my system is made up of suppose n particles. So each particle will have their position vector. So here I am writing the particle 1, 2 up to n. So suppose the first particle is having their position vector r1, the second particle is having its position vector r2, and the nth particle is having its position vector rn. Similarly, if you want to find their linear momentum, then their linear momentum will be p1, p2 and pn respectively. Now, with the help of this position vector and this linear momentum, I can find out the angular momentum for the individual particles. So, the linear or angular momentum of the first particle is L1, for second particle is L2, and for nth particle that is Ln vector. So, if I want to find out the total angular momentum of the system, then we know it is the vector sum of the individual ones. So now I am writing the total angular momentum of the system. I am denoting this total angular momentum as capital L. So this will be L1 vector plus L2 vector plus so and so Ln vector, and this is your first equation for this analysis. Now what I am doing, I am differentiating this equation with respect to time. So the left hand side will be d capital L by dt, that is equals to dl1 vector by dt plus dl2 vector by dt plus so and so dln vector by dt. But as per the relation we have obtained in the above analysis, that dl by dt means the rate of change of angular momentum with respect to time is the torque. So this quantity is the torque for the first particle, this is for second particle, and so this is for the nth particle, and hence I can write down the right hand side as tau 1 plus tau 2 plus so and so tau n, and I can generally write the left hand side or right hand side as dl by dt is equals to tau, and this is the total torque of the system, remember. Now in the statement I can write down this equation number 2 as the rate of change of angular momentum of a system of particles with respect to time. This particular quantity you have to remember is equal to the resultant external torque. See, I have used the external word over here because there is internal force, or the resultant internal force or torque is 0. So here the internal word you have to correct and you have to write down external. And why I have cancelled out this internal word? The reason I have told you. So this is about the angular momentum on the system of particles. Now we will see the angular momentum of a rigid body. Let's study the angular momentum of a rigid body. Now, why it is necessary to study this rigid body concept separately? Because inside the rigid body, the relative distance between the particles remain invariant. So it is necessary that we should have to study this particular topic separately. And if you want to know the motion, the actual motion of the particles of the rigid body, perform uniform circular motion, or as it not perform a uniform, then it will perform a circular motion in a plane that is perpendicular to the rotational axis. Now suppose if we take the center of the circular path of every particle as a reference point. So suppose I have considered this as a reference point, then the angular momentum of the particle will be also along the rotational axis. And so I can find out the total angular momentum of the particles of a rigid body. And that is given by vector L is equals to L1 vector plus L2 vector plus so and so Ln vector. That is the equation 1. Now I am substituting the values of individual angular momentum. That means the value of L1 is R1 cross P1. plus the angular momentum of the second particle of the rigid body is R2 cross P2 plus so and so Rn cross Pn, and this is the total angular momentum. Now, here the vector R and vector P, they are mutually perpendicular. So I can write down as this R perpendicular to P. So I can write down the magnitude of L. So the angle between R and P will be 90 degree and sine 90 is 1. So I can easily write down the magnitude of L. Therefore, mode of L equals to R1P1 plus R2P2 plus so and so Rn Pn. So this is the equation number 2. Here these quantities are coming from the actual relation L is equals to R cross P. So you can write down this as Rp sin theta. But here we have assumed that the value of theta is 90. So Rp sin 90, that is equals to Rp, because sin 90 is equals to 1. And for L1 I have used the subscript R1 P1. Now, substituting the value of P is equals to mv in equation number 2. So we will get modulus of L, that is equals to R1 M1 V1 plus R2 M2 V2 plus so and so Rn Mn Vn, and that is equation number 3. Now, we are knowing the value of linear velocity, that is related with the angular velocity by relation see each and every point you should remember, because you are going to write down the full theory in your examination part or in proper descriptive part. So the relation is given by V is equals to R omega, that we have already found, and I am substituting this relation in equation number 3, and hence my value for modulus of L, that is equals to M1. Now R1 square, because R into R, that is R square. So here R1 into R1 is R1 square plus M2 R2 square omega. See, I have not used the subscript in the case of omega because the angular velocity is remaining constant for all the particles, and I am expanding these assumptions to the nth particle, so mn Rn square omega. If I am replacing this equation by taking the value of angular velocity common, so we will get m1 r1 square plus m2 r2 square plus so and so mn rn square into omega. And here this is the value I am consider over here as capital I, this bracket value. So modulus of L is equals to I. And see, this is the magnitude of angular velocity, omega vector. And this is my equation number 4, where this I is what I am explaining you. Here I is equals to m1 r1 square plus m2 r2 square plus so and so mn rn square. That is equals to summation over I mi ri square, where I stands for 1 to n. And this I is called the moment of inertia. And this is for rigid body only. Here if you see the direction of omega and the direction of angular momentum, and that are parallel to the rotational axis. And so as they are parallel, I can consider this momentum or the moment of inertia as a scalar quantity, because if you want to give the dot product, then one quantity should be scalar and another quantity as vector. Then the resultant will be the vector quantity. Now I am differentiating the equation number 4 with respect to time. Therefore, dl by dt. Now this moment of inertia will not change with respect to time, so that is constant, but the angular velocity is changing with respect to time. So dl by dt is equals to I d omega vector by dt. This change in angular velocity with respect to time is the angular acceleration alpha. And so I can simplify this equation as I alpha vector, and this I alpha is what, or this dl by dt is what? The torque means tau. So this is another relation between torque and acceleration. Now, when the value of torque is 0, then either I is equals to 0 or alpha is equals to 0, but the value of I will be not 0, and hence the value of alpha is equals to 0. And if you compare with this equation, then the right hand side is 0. That means the quantity which is differentiated, so that quantity will be constant. And so I can write down one statement from this, that if the resultant acting torque acting on the rigid body is 0, then the angular momentum of the rigid body is constant. And this particular statement is known as the law of conservation of angular momentum, because in this criteria, angular momentum is conserved. So with this our angular momentum topic is over, and we will now study the representation for angular momentum.